assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this problem, we are asked to find the radioactivity of 1 kilograms of carbon that was present in the bone of an animal that died 60,000 years ago. The problem is asking what the activity level is of carbon-14 today. Well, looking at Appendix B, we see that carbon-14 has a half-life of 5,730 years. Another fact from the text that we need here is the fraction of carbon-14 that is present in all organic matter during life, and that's actually due to a cosmic process. And I'm sorry, that fraction that we're looking for is the fraction of carbon-14 to regular carbon-12. That fraction is very small. It's on the order of 10 to the negative 12, and it only occurs during life. So a given in this problem is that there is 1 kilogram of carbon in the animal's bone at the time of death. So we can find out the initial amount of carbon-14 isotope using this proportion that we found in the text. And that turns out to be 1.3 times 10 to the negative 12 kilograms for 1 kilogram of carbon. Next, we need to find out how many atoms, carbon-14 atoms, there are, or there was initially at the time of the animal's death. That we can find by looking up the atomic mass in terms of atomic mass units of carbon-14 and multiplying that by the conversion factor for atomic units to kilograms. That product we are going to divide into the 1.3 times 10 to the negative 12 kilograms, and we're left with, initially, there was 5.593 times 10 to the 13th carbon-14 atoms present in the animal at the time of death. The next thing we need to find in order to solve this problem is the decay rate. And so I've neglected to mention so far that the strategy we're doing to solve this problem is using the decay rate equation, or the decay amount equation. That's a form of exponential decay. We determined the initial amount of carbon-14 in the previous step. Now we need to find the decay rate that goes in the argument of the exponential. Recall that the decay rate is the natural log of 2 divided by the half-life. The decimal equivalent of the natural log of 2 is 0.693. The half-life we need to express in terms of seconds. We know that from Appendix B that the half-life of carbon-14 is 5,730 years. And there are 365 days in a year, and there are 86,400 seconds in a day. Plugging these numbers into this relationship, we find a decay rate of 3.835 times 10 to the negative 12 reciprocal seconds. Now, in order to find the amount of carbon-14 left after it's been decaying over many years, 60,000 years ago to be exact, we plug in 60,000 years in terms of seconds in our decay rate equation above. And doing that and using the decay constant we just found and the amount of carbon-14 initially in terms of number of nuclei, we find that after 60,000 years, there is 3.946 times 10 to the 10 nuclei left in the bone. And the final step is to find the activity based on that amount of nuclei, or that number of nuclei present today. And to do that, we simply take the product of the decay constant that we found earlier times the amount of carbon-12 in number of nuclei today, which we just found in the previous step. Taking that product, 3.835 times 10 to the negative 12 reciprocal seconds times 3.946 times 10 to the 10th nuclei, we have a activity of 0.1513 decays per second, which for two or one significant figure, we express as 0.2 decays per second, which matches the answer in the book. And trying to box this here. There we go. That concludes our problem.